Alright, let me check the health of the stream here. Alright, let me check the health. Alright, so I think we're good. Let me get one more over here. All right. All right, we talked about this. We did problems with it. Let me just go ahead and copy the set of equations and put, here, do this. Let's do this one. Oh, okay. Well, okay. Do this. So we're not there. So there's our first equation. The second equation we're going to focus on is down in here in the acceleration. We will work a problem all the way through that has velocity and acceleration. So the difference here in the acceleration component is this. If you look at these, what you've got is an extra term here, which is a tangential term. So in other words, everything here is normal, everything here is normal. However, if you take the perspective that you are sitting on a, here, let me change the color here. If you're sitting at this point, there are two things that can happen. This rod here, the acceleration that you see as if you are pinned to the ground, would be such that you would have an acceleration around you. If it were this direction, you would have an acceleration tangential, and you would have a centrifugal component. And so what he's calling, that's what he's calling his normal, the centrifugal component. The tangential is the component along here. As it turns out, that the acceleration here, let me get rid of some of these terms. The acceleration basically ends up being exactly like this. I think we talked about this in a previous lecture, which we went through it. Essentially, this term comes from the result that if you're taking the derivative and you realize the velocity of, in this case, B relative to A, excuse me, is equal to omega cross RBA, then derivative of this component, velocity of B relative to A, would be derivative of omega t cross RBA. This term is actually that term. But it's also a term in which omega cross derivative of, hang on just a second, you had B to A, that's what you had to get, sorry, derivative B to A with respect to time. This term, believe it or not, is actually this term. So in fact, this last term is this one, in which if you write it out down here, becomes omega cross parentheses this part, because this is that. Omega cross R B to A. Now, in a sense, if you look at this term, this always ends up being that. And I think we talked about that before, because if you're looking at something, it's rotating this way. This component, this is the velocity of B with respect to A, and that happens to be what's in the parentheses here. You take that and cross with the vector here, so now you're crossing a vector which is coming towards you, and if you wanted to represent it in 3D, maybe it's coming out of the plane. So here is your omega. You take this vector, cross it with that vector. If you do, you're going to get a vector that runs back this way, hence the minus. So with all this, let's go in now and copy this one. Go back over here, maybe drop it right there. We probably will move these to the right a little bit after we pick a problem. So let's go and pick a problem. And we'll go through the whole thing. So it has to be at the end of this chapter, because this section, because this is the one where they'll give us an alpha. So let's just go in and pick one. Set up the relative between points here. Okay. But he does, oh yeah, he does. Okay, so he's given us omega, he gives us accelerations. Let's see, what do we want to do? Which one do we want to do? Let's start with this one, say. I don't want to just set up the relative acceleration. I want to go ahead and find all the information here. So let's start with this one. So if we head off to this one, first thing I'm going to do is I'm going to go ahead and put it somewhere. I may actually move it. Pretty obvious I'm going to move things. Let's move this over here. Let's move this over here. And in addition, let's make it a little bit bigger so the type's about the same. And what we're going to do here is I'm going to do a copy and I'm going to do a paste. What I'm going to do is a little portion over here in which I'm going to be doing the instant center here. Let's go ahead and do that real quick. Okay. So I am given this information. So I know from this one at least, the velocity of point A is is going down, I can figure it out. It's 4 times that. Velocity is equal to 4, or here, let me do it this way, omega r, which is 4 radians per second, and 0.5 meters, gives me 2 meters per second going down. Now what I'll do, I'll go off and take a perpendicular to it and draw that line. Next thing, I know this is either moving this way, which I think that's what it's going to do, but it could be moving the other way. Either way, draw a perpendicular to it, and that is the location of your instant center. Okay, so now we have an incredibly simple triangle. This is 30, this is 2, so this distance out here becomes 2 cosine 30. This distance here becomes 2 sine of 30. So that will become 1, but I want to do it exact. Give me a second. So okay, 2 goes cosine degree of 30, 1.7321. And this one will be 1, but I'm going to go ahead and do the calculation. And that is sine of degree 30, which is 1. So now, think of it like this. I no longer am concerned about this rod right here. But what I do have is I have something very interesting. I have essentially, think of it as a rigid piece of triangular metal, which happens to be green, and it is rotating this way. Omega, now he gave us omega, and we're going to check him. V is equal to omega r. So any point connected to this rotation here, the velocity is determinable by taking the r to it. So in other words, velocity at point A happens to be 2. The omega happens to be, let's assume we don't know it right now, and assume we know the r, which is 1.7321. So omega will be 2 divided by 1.7321. 1.1547, 1.1547, which is what he gave us here. Now, what's the velocity at point B? Now that we know this is omega, well, again, B is on this piece of green triangle right down here, and so the velocity of point B would be equal to omega times a different r, this r being the distance from the instant center to the point, 1.1547. 0.47 times 1 tells me that the velocity of that point is like so. Now, I know it's correct this way because the thing is rotating like this, and if it is rotating, then all these points are like that. In other words, go to any particular point, this point would have a velocity like this. This point on the rod would have a velocity like this. This point on the rod would have a velocity like this, where all these are 90 degrees. Now these two, this one and this one, aren't on the rod. And if you go down to here, 90 degrees going to the left, right, like that. So that gives us the velocities off the instant center. Okay, so what I'm going to do, I'm going to go in and I'm going to sort of accentuate this one, although we gave it to us. We're double checking. Now let's go back and do the velocities. Even though everything's there, we're going to do the velocities off of this equation. So what I'm going to do, I think, is swap these two. Now, I really should have copied this equation with, it's too late now, I should have copied it with an AB here and an AB here, because there are many omegas and alphas that could happen through a linkage like this. So let's start with the velocities. We already know this. Okay, velocity A. Now, I'm switching these, A and B and A and B, but I'm going to write it down here and you'll see what I mean. Velocity A is equal to velocity A relative to B. I'm sorry, we didn't label this. This should be like P for pin. Plus velocity of the pin. Pin, 0. This becomes omega AP, which is this. This is the link PA or AP crossed RAP. What is this? Sit on the pin, draw a vector this way. When you're doing these are all vector equations, so it's best to set up a little symbol like this. And then, not too surprising, you'll end up with, okay, this direction is counterclockwise. It is also positive, so it's a 4. I didn't talk about this vector yet, but this vector R, A to P, has only an I component. It doesn't go up or down. So we end cofactor expansion, or we could rely now on a vector component using octave. Oops. We could set up a vector, omega, just let's call it AP, is equal to a vector of 0, 0, and 4. Then we have a vector RAP, a vector that would be minus 0.5, 0, 0. Oops. Then we could do a cross cross of omega AP with RAP. And we get this 0 I minus 2J plus 0K. How do we get that? I'll do this one particular time, and that is we do the I component, cofactor expansion, meaning this vector or this matrix ends up there, 0, 4, 4, 0. Minus J, cofactor expansion here would be this, move over to here, 0, minus 0.5, minus 0.5, 4, 0, and then cofactor expansion here, through this, move over to right there, 0, 0, minus 0.5, 0, this, okay, this and this give you 0, that, and that give you 0, that, and this, which becomes a minus, and a minus. So a minus because of this, minus because of that, and a minus because of the direction. This is the minus, and this one right here is the plus. So what you get is 4 times 2 gives you your 2. So this is the velocity of A, and that's exactly what you would expect it to go straight down and go on from there. Now that I've got all that, I am going to take this, kind of shrink it down, because I can grow it if need be, move it over here to the side, and then I'll put a funny little box around it to indicate it's its own entity, and we'll take off and do the next part. Velocity of B is equal to velocity of B relative to A plus velocity of A. This is nothing more than minus 2J. So we've already determined it right here. This, now I'm going to assume for the moment that maybe I don't know that, and we're going to find it. Now I know that he gave it to us, but these were slightly different kind of problems in which they did give them to you. Now, omega AB, which is in fact this, but we're not going to claim we know it. We're going to, this is usually not given. This is something to find. Actually, that should have been a vector there. Cross R, okay, B, A, minus 2J, which I'll just start carrying this down for the ride. What is this? Hang on. Sorry about that. This is a vector which starts at A and proceeds down to B. Well, at this particular point, I'm going to kind of make use of something I already worked on, and that is that I found this distance and I found that distance. So, taking a side issue here, RBA is equal to minus 1.73 2, 1 right here. Two, 1, I, and then it goes down. This distance here is 1, 1, J. So we're going to list this now as I, J, and K. I'm going to show you a little trick here in a second. I am going to assume that omega AB is unknown, minus 1.7321, minus 1, and 0. Okay, so the question is what is this? Now here's what I'm going to do. Omega AB, I, J, K. Why can I take this out? Well, the reason I can take this out is because the vector omega AB is equal to omega AB, the scalar value of that, times a vector which is 0I, 0J, plus 1K. Now, what I can do is put this vector in 0, 0, 1, and leave the omega out here. Think about that for a minute. This is totally legal. And then you can put in 1.7321, 1, and 0. Now, in here, I have only numbers, which means I can go to this. What is that highlighted for? Okay. All right. So this I can go to here, which is, okay, make AB equaling to 0, 0, and 1. Oh. Why is it not doing this? Make it AB equal to 0, 0, and 1. Or BA equal to minus 1.7321 minus 1 and a 0. Now I can do a cross of omega AB with RBA, and I end up with 1 omega. And you have to realize what I'm going to do here. I'm going to go ahead and do this. Omega AB times the result of this, which is 1I minus 1.7321J plus 0K. Now, let's stare at this for a minute and realize, okay, 1I minus 1J. So, like this, minus J, which puts me perpendicular. This is the velocity, which is perpendicular to this. This is as if this thing is pinned. I have not included my 2 yet. Now, the other thing is dot product. Okay, your check. This times this plus this times that should equal 0. Now, the other one is it's perpendicular to both this times that plus this times that plus this times that. That's pretty obvious because there's a 0 in every single one. So now, my end result is velocity of B, which came all the way down to here, equals to omega AB times 1I. How about I just combine these now? 1.7321 omega AB J minus 2J. I also know that the velocity of B is going to be either going this way or this way. I'm going to assume it to the right. So I'm going to assume this to the right. Going to the right, that means it's plus. Now I know my result over here showed it was going to the left. Minus 1.7321 omega AB J minus 2J. Now, how do I solve this? Take my I components, take my J components. So my I components are going to be velocity of B, oops, that's the scalar, is equal to omega AB. My J components are going to be 0 is equal to minus 1.7321 omega AB minus 2. That's going to tell me omega AB is equal to, and something is wrong here, I think, but let me check it out. Minus 2 over 1.7321, or 1.1547 minus meaning looks a little uneasy right now. This is positive, so this means that omega AB is equal to 1.1547 going the other way. Let's see. Did he even mention it? This direction? No, he did not, but it is going clockwise. So it is going in the direction or the rotation of a clock, which is in fact what we have. This is a clockwise rotation, so we're correct. Now, it turns out, since that's a minus sign, we put it in here as a minus sign. And what we see is velocity of B is equal to minus 1.1547. That is going that way. So, in fact, the velocity of B is actually going equal to 1.1547 going back this way. Now, did we get that here? Yes, we got that here. Now, all this is a moot point because the problem he gave, he expected you to start from here and work your way through the accelerations. Why? Because he gave you this, he gave you these, and he expects you to work through this. It turns out he gave you enough information, meaning this, to skip over the velocities and work straight through the acceleration. So what I'm going to do now is, I think I'm going to copy the thing again, and I'm going to work my way through just the acceleration. So again, to kind of tidy it up here, put myself right here, and now I'm going to go back up here if it'll listen to me, and I'm going to grab this equation. I'm going to go back down here, and I'm going to grab this. And now I'm going to go straight after the acceleration. Now, The A and B may be different, so I'm got to go back and I got to put a pin here. So the acceleration of A is equal to, and I like to write this first, alpha of AP, the pin, crossed with R, A, P, minus omega, the scalar value of AP times R, AP plus the acceleration of the pin. The pin itself is fixed, so in fact this term is 0. Turns out the acceleration of A, point A right here, it's going to have a centrifugal component and it's going to have a tangential component. It becomes, okay, so now I am going to go back and look at the coordinates and say this is a positive rotation. Both of these are positive. So I say I, J, K, 0, 0. What is alpha? This one, 8 radians per second squared. That is an acceleration, so he should have written this as omega, and this is alpha. Now, your R vector, it goes from here back to here. In other words, you see it twice here. See this vector here and here, and it is a vector that starts at P, puts the airhead at A, and it becomes R, A, O to the P is equal to minus 0.5 times I, and that's it. So now you take this, minus 0.5, 0, 0, that's all you got. We'll do that in a minute. Omega squared minus omega squared. Omega squared is 4 squared, that's this 4. So this is AP and AP because it's specific to the link here. It's not on this link. So that vector, now here's what you can do. To find this, you can look at this row. And you can say minus 0.5 I plus 0 J plus 0 K. In other words, this one here, this one's from here, and this one's from here. So you look at that, first thing you see is now the only one that's going to have a component in this term is going to be if you take this out and take this out, because no matter what you do with the others, if you take this one out and this one out, you're left with a 0 here and here. If you take this one out and you take this one out, you're left with a 0 here and here. So the only thing you get is a J and a 0 minus 0.5. Well, let me back it up. Minus J. And then an 8 and a 0. So what you end up with is plus minus this term, but it has a minus, and it has a minus out front, so you get minus 4J. Now, think about this. Let's just stare at this for a minute. This is the tangential acceleration of that point. And that's telling us it's going down at 4. This is alpha times that will give us 4. So in fact, this makes perfect sense. This term, on the other hand, becomes 16 times minus 0.5 I. Okay, so you get a minus and a minus, you get a plus, and half of 16 is 8 I. This term is actually directed, the acceleration that is directed back this direction, centrifugal acceleration. And you can look at this two ways. It's the v squared over r, where v squared is 2, right? Wasn't it 2? It's 2, and r of 0.5 squared becomes 4 over 0.5, which turns around and becomes 8, is what that is. So, in fact, this is the acceleration of A. It had two components. It had a tangential, and it had a centrifugal. So, now becomes the real fun. The real fun is in dealing with this member, AB. So in order to highlight that, I am going to go back here, and this time I am going to do, let's see, snippet. Okay, first I got to do a new. All right. I am going to do my best to look at that. Now, I'll go back over here. I'm going to go down here and just sort of drop it. Now, I am stuck with something interesting. Okay, let's look at this. Acceleration of B is equal to acceleration of B relative to A, which has two components, which has the alpha AB cos R BA minus the omega of AB, and I'll just go ahead and use this one, squared times R, excuse me, and then plus acceleration of A. Now, we got this a minute ago, but now we're going to focus on this. If we look at this equation, we are only interested in this link. I got a little bit of acceleration this way, a little bit of acceleration this way. What's happening over here at B is I only have acceleration like this or like that. It's either accelerating or decelerating. I don't know which direction. Now, with this, you can't use instant centers. But what I can do is make an assumption that it's accelerating to the right, A, B, I. I have to either do that or make an assumption that it's accelerating to the left, but it cannot be accelerating up or down because it's in this cylinder here. Equals to. Now, what I'm going to do, take out the scalar version, and I'm going to do I, J, and K, 0, 0, and 1, R, B, take a vector, start it at A, go to B, and that's that vector. So again, R, B, A, which was the same as up there a few minutes ago, minus 1.7321 I minus 1J. It's the same thing, minus 1.7321 minus 1, 0. That comes from here, and then minus. Okay, so I can go ahead and put this in. This value is that value, which would be 1.15. And I had some extra values, but I'm not going to put them. Then, again, I'm copying this straight to put here. Why? Because this and this are the same. So, minus 1.7321I minus J plus 0K. So I'm going to drop the 0K. Now, what I also have to include is this term, minus 4J. Actually, let me do this. I like to do it where I have the I first. Now, believe it or not, and this is something that occurs every single time, let's go up and look, and this is the beauty that I can do here. I'm going to copy this portion of the equation that I had a minute ago. Do a copy. I'm going to delete it in a minute, but I'm just going to copy it right over here to the right, just so I can inspect it. It's a little big, so I'm going to shrink it. If I can get my thing down here, go ahead and use a let's stare at this one. What we're just doing is a comparison here, and I don't know why. Well, I'm only a few minutes to the end, so I'm having trouble. I'm going to have to drop it down and come out. So I'm going to pick up exactly here, and I'll label it. As a matter of fact, I'll label it and pick it up exactly here. But I am very confused here. Go up here. Okay. Okay, so I'm going to drop the stream. We'll pick it up on Monday right here.